So now we have so now we have talked about some definitions for mixed strategy Nash equilibrium. We've also talked about um, some. Well, we started with talking about symmetry. That's going to be more useful in the next lecture. Um, but now that we have some grounding on what a mixed strategy Nash equilibrium is, what mixed strategies are, let's do some examples. Because this last video you saw was pretty heavy. Okay. We'll start with this game that we talked about earlier. Top left. Oh, sorry. Top, bottom, left, right, C2, P1, 2, comma 1, 0, comma 0. Okay. Um, this is a game in which you have two Nash equilibria in pure strategies. You have, um, just write out the best responses first. So our Nash equilibria, and in order to denote that they're pure strategy Nash equilibria, we just add a P and an S. Okay, pure strategy. Okay. These are the sets top left and bottom right. The feature of this game that makes it interesting is that it's a coordination game in which you have these 2 points at which players could coordinate. At top left, this coordination benefits player one. At bottom right, this coordination benefits player two. And it's asymmetric in that sense. Um, And so there's this sense of bit of a push and pull between the two players about where to coordinate. If you play this game out in the lab, you can see in the chats between two players that there's that kind of push and pull, that kind of negotiation happening. And it captures a situation in which working together is beneficial, um, but the benefits can be asymmetrically spread between two sides. So a joint venture with asymmetric benefits, or even a relationship with asymmetric benefits. But there's also going to be an equilibrium of this game in which the benefits are a bit more symmetric. Um, and that one will be the mixed strategy Nash equilibrium here. Um, so suppose I give you this payoff matrix without the best responses, because when I pose a question, I'm typically not going to write out the best responses for you. Um, and I ask you to find all mixed strategy Nash equilibria. Okay. How do you go about doing that? Well, the first thing you do is you suppose that T1 chooses T with probability T, where P is some number between 0 and 1. You also suppose that P2 chooses L with probability Q, where Q is some number between 0 and 1. Okay, so you have some P here, you have some Q here. Notice I didn't suppose anything about the probability with which player 1 chooses B, because that will simply be 1 minus P, or the probability with which player 2 chooses R, which will simply be 1 minus Q. So finding MSNEs simply boils down to finding P star, Q star that are stable. Right, so that is what you want to do. You want to find all the P star, Q star, the P and Q combinations that are stable. The star is just what we add to denote equilibrium objects to make them feel a bit more special because they're stable. Okay, um, so let's do that. How do we find equilibrium when we have this kind of situation? So this is going to be quite similar to the joint venture example or the Cournot example, or even the Bertrand example that we did earlier. Step one will be to figure out what is our actual utility function here? What is our utility as a function of the choices that these other players can make? Okay, now here, even though this is a simple 2 by 2 matrix, the choices available to players. So for player one, the choice is every possible value of P that is between 0 and 1. So it's a continuous choice, right? It's continuous in the same way that Cournot, that quantity choice is a continuous choice. Same for player two. The choice is now a continuum, is now from a continuum. So you can have a value of Q that is equal to 0, 0.001, 0.01234567, whatever you like. Any number between 0 and 1 is a valid choice for player two. So step one will be to define our utilities, in this case, expected utilities. Step two will be to find the best responses. Same steps as we did earlier. Okay, so nothing new here. So find utilities, best responses. You know what step three is? Find where those best responses overlap. Where those best responses overlap, you have a Nash equilibrium. Just as in the Bertrand case, we're going to map out the best responses, so plot them in a graph to make life easier for us. And that's it. So let's get to it. Start with the utilities. Okay, so I want to have these four numbers. I want the expected utility that player one gets from choosing T, taking as given Q, the expected utility that player one gets from choosing B, taking the Q as given, the expected utility that player two gets from choosing L, taking the P as a given, and the expected utility that player two gets from choosing R, taking player one's choice of P as given. Okay, I'm going to zoom out a little bit. Okay. So for player one, when player one chooses T, player one is taking this Q as a given. Okay. So player one gets this value 2 with the probability Q, and this value 0 with the probability 1 minus Q. So it is 2 times Q plus 0 times 1 minus Q, which is 2Q. When player one chooses B, player one gets this 0 with the probability Q, and this 1 with the probability 1 minus Q. Right? Because player 2 chooses L with the probability Q and R with the probability 1 minus Q. Okay. Now let's look at player 2's choices. When player 2 is evaluating the value that she would earn by choosing L, player 2 is going to take as given that player 1 chooses P with the probability P and B with the probability 1 minus P. So when player 2 chooses L, player 2 gets this 1 with the probability P and this 0 with the probability 1 minus P. When player 2 chooses R, player 2 gets 0 with the probability P, 2 with the probability 1 minus P. Okay. So now we have figured out the utility that each of these players will get, taking as given Q, taking as given P. This is going to be what we need in order to find best responses. So let's look at these two values first. uh, to figure out player one's best responses as a function of Q. Okay, so what is BR1 as a function of Q? Okay, let's start with a low value of Q. When Q is 0, player 1 gets nothing from choosing top, because that's 2 times 0, and player 1 gets everything, 1 minus Q, 1 minus 0, from choosing B. So player 1 will definitely choose B. Okay, so let me do some rough work here on the side. Okay. E U1 from T given Q will be less than, well, let's just call it less than E U1 from B given Q, if and only if 2 times Q is less than 1 minus Q, 3Q less than 1. So I just added Q on both sides right now. Now I divide both sides by 3 to get Q less than 1/3. So when Q is less than 1/3, I have to choose B and bottom and not top as player 1. Right, so this becomes, my best response is just B. Oh, sorry. By the way, choosing B means the same thing as choosing P equal to 0. Okay, a choice of B means that player 1 chooses B and not T. Okay, so okay. So if Q is less than 1/3, I choose B, P equal to 0. What happens when Q is greater than 1/3? I just flip signs. When Q is greater than 1/3, then that means that I choose E equal to 1. What happens when Q is equal to 1/3? When Q is equal to 1/3, then that means that my expected utility as player 1 is exactly the same whether I choose top or bottom. It's also going to be exactly the same regardless of how I mix between choosing top and bottom. So when Q is equal to 1/3, my expected utility from choosing top is going to be 2/3. My expected utility from choosing bottom is also going to be 2/3. So either way, whether I choose top or bottom or any mix between the two, I'm going to get the exact same expected utility of 2/3. So any value of P that is between 0 and 1 will be a best response for player 1 if Q equals 1/3. Okay, so this is the part which is going to be trickiest. When Q is exactly 1/3, then player 2 has chosen to mix between left and right to leave player 1 just indifferent between choosing top and bottom, which is what allows any mix between top and bottom being chosen by player 1 to become a best response for player 1. Okay. Let us also write out the best responses for player 2. So I'm going to copy these 2 lines out again. Paste them here. And that's going to help us think about best responses for player 2. Okay. Let's just quickly do the same exercise where we did some rough work. EU2 L given P is greater than E. Well, let's just do less than again. Less than E U2 R given P. If and only if P is less than 2 minus 2P. So I just plugged values in. Now let's add 2p on both sides. So 3 times p is less than 2. Let's divide both sides by 3. P is less than 2/3. Okay, so my best responses for player 2 will be a function of this choice of p. When p is less than 2/3, it is better for player 1 to choose R and not L, because the expected utility from L is lower. Choosing R all the time means the same thing as choosing Q equal to 0. Right? Q equals 0 means you choose R with probability 1. Okay. Similarly, if P is greater than 2/3, then you have this condition. And so L is better, which means that player 1 chooses Q equals 1. And if P is equal to 2/3, then you end up with this condition. And so, again, the expected utility from choosing left, same as expected utility from choosing right. And so any value of Q between 0 and 1 becomes the best response for player 2. Okay. What I'm going to do is I'm going to copy this guy again, bring it down there. Now I'm going to make a graph. Let's suppose we have BR2 of P on the y-axis and P on the x-axis. Okay, this is 1, this is 1, these are zeros. Okay. When P is less than 2/3, Q equals 0. Saw this in the light green. When P is less than 2/3, Q is 0. When P is greater than 2/3, Q is 1. P is equal to 2/3. Then when P is greater than 2/3. Okay. Let's draw in red BR1 of Q. And have Q here. So when Q is less than 1/3, T is equal to 0. That is this. Let's go up until 1/3. When Q is exactly equal to 1/3, P can take any value between 0 and 1. So that is this part. So when Q is exactly 1/3, P equal to 0 is the best response, P equals 0.75 is the best response, everything is the best response. And when P equals 1, when Q is greater than 1/3, so for these values of Q, my best response has to be P equal to 1. Do you see how these best responses overlap 3 times? One is at P star, Q star equal to 0, 0. One is at 2/3, 1/3. And one is at 1, 1. These are our mixed strategy Nash equilibria, this set. Okay. The 0, 0 corresponds to bottom right, and the 1, 1 corresponds to top left. So the pure strategy Nash equilibria that we had earlier, those are still here in the form of mixed strategy Nash equilibria. I'm going to do one more example. That'll be in the next video. See you.